Okay, so I had a bunch of people come to me, Mr. Coderre, I'm so sorry I didn't get the notes printed. Okay, there's no big deal if you don't have the notes printed right now. You don't need them printed. It's just convenient, especially if that's the way you want to take notes. Have the printed copy and add to it. If you don't have them copied at any point, that's okay. You don't have to print them. Okay, it's just lots of people like to have them there, and the sooner you have them there, the more you can get into your system of whatever you're going to use. You absolutely don't have to have them printed. Now, for the worksheet package, if you don't have that this week, you'll probably be fine, but next week when we're using it quite a bit more, it'll be a lot more convenient to have it. Now, again, is that something you have to have printed? No, but it's more convenient because I can't show all of the questions on the smartboard at once. So maybe you're done with the stuff I've got on the board and I'm not ready to scroll up yet and you're waiting. Okay, it's that kind of situation that it's nice to have them printed for. Okay, in case, I also had a few people emailing me saying, I can't find them, Mr. Coderre, where are they or which ones do I need? So if you're in our Google Classroom, they're in the class work tab and they are here under worksheets, worksheet packages and other materials. Okay, you just go here and it'll say your name and it'll tell you which unit it's for. There's no workbook for biology, so there's only 3. Okay, and you need the first one here, the Unit 1 Chemistry Worksheet Package. Okay, that's the one we'll be using for the next month and a half or so. The notes packages, remember they're up here. Okay, and you can they'll say the same thing. It'll say your name with the units. You need the Unit 1 one if you're going to print them. Okay, but that's where you can find them all. Certainly you'll want those when you're studying. Okay, that's your textbook. We don't use a textbook in this course. Okay, so the notes you take and those notes packages, that's what you use to study. Okay, there actually is a textbook, but it's crap, so we don't use it. Okay, all right, everyone okay with that? Okay, so don't panic if you don't have them printed. I don't have a printer at home. It's fine. Okay, we'll make it all work. It'll all be fine. Okay. All right. So if you don't have those already copied down, make sure you get them copied down. I'm just going to get the attendance done here real quick, and then we're going to talk about these. Okay, so we started talking just a little bit about these yesterday, but we didn't get very far into it. Okay, and we said that this is generally credited to John Dalton, okay, coming up with the atomic theory, even though the first point of the atomic theory is actually Democritus' idea, okay, not Dalton's, but we still go with it. Okay, and it says that all matter, that is absolutely everything, okay, is composed of tiny indivisible particles called atoms. Okay, remember that they're indivisible, that means not cuttable, not invisible. You can't see them even though they're too small for us to see. They're not actually invisible. Okay, otherwise you'd be able to see through everything. Okay, now the second point is important because it talks about how the structure of each atom is what gives it its unique properties. And we talked a little bit about that yesterday when I used the example of I have a block of lead and I have some oxygen. Lead has way different properties than oxygen does because a lead atom is always going to have 82 protons, whereas an oxygen atom is always going to have 8 protons. I said atoms, didn't I? 82 protons, whereas an oxygen atom has 8 protons instead. Okay, that's what's going to give them their different properties. It's the number of protons and thus the structure of each atom that dictates the physical properties. So for number 2 here, it says atoms of the same element are identical. So every atom in that chunk of lead that we talked about yesterday is the same. It has 82 protons. Now, there might be the odd one in there that's got a different number of neutrons. We call those isotopes, but for all intents and purposes, they're all the same. Okay. And the atoms of any one element are different from those of any other element. That's the oxygen and lead thing we talked about yesterday. Now, point number 3. Point number 3 talks about what can happen with atoms. Okay, so it says atoms can combine in simple whole number ratios with one another to form compounds. This is kind of what the alchemists were doing, but they didn't realize it was what they were doing. Okay, so if I'm looking at this, if I'm an alchemist, I'm saying, all right, I added A and B together, and I got C. Okay, that's why they thought they could add something to lead and turn it into gold, even though they would actually have to subtract according to the structure of the atoms. But okay, that's what they thought they could do. All right, well, what modern chemistry says is that if I take two hydrogen, okay, and I react it with oxygen, I can get water. Now, I do have to balance that so that I have the right number of everything, but if I took 2 molecules of hydrogen, that would be 4 hydrogen atoms, and reacted it with 1 molecule of oxygen, that's 2 oxygen atoms, I would get 2 molecules of water. Okay, it's a whole number ratio, 2 hydrogens to 1 oxygen. Okay, I would never reduce that down to something like this. Right? That's not a whole number ratio anymore. Okay, can I have half an oxygen atom?
No.
Well, it's not oxygen anymore. If I have half an oxygen atom, I have beryllium. Right? Because it would have 4 protons then. Okay, so it'd be different. So you're never going to have a fraction when you're writing a compound. It's always going to be whole number ratios, 1 to 1, 1 to 3, 3 to 2, whatever it happens to be. They're always going to be whole numbers. Making sense? Okay. Now, point number 4 was the final nail in the alchemy coffin. Okay, the alchemy saying, I can turn lead into gold, I can do this, I can do that. Okay, this was the final nail in the coffin. Point number 4 tells us, here's what happens in a chemical reaction, and here's what can never happen in a chemical reaction. Okay, so chemical reactions occur when atoms are separated. So let's say I had this compound. Okay, I could separate that into hydrogen and nitrogen. I could pull the hydrogen and the nitrogen apart and go from having nitrogen trihydride to having hydrogen gas and nitrogen gas. All right, I've separated the atoms. Okay, so that can happen in a chemical reaction. Okay, they can be joined. So like this reaction, I would take my hydrogen and my oxygen, I would join them together to make water. That I can do. Okay, I can also rearrange them. Okay, and I showed you that one yesterday with the potassium iodide and the lead nitrate. Okay? In all of those reactions, do I ever make a new element?
No.
No. Okay? I make new compounds, I make new substances, but I'm always using the same building blocks that I started with. I can't remember if it was your class or my period 2 class, but I use the example of, let's say you have like a wooden pallet sitting on the ground at home, okay? And you decide you need to build a doghouse. So you take the pallet apart and you build a doghouse out of it. It's the same wood, okay? It's the same material, it just looks different now. Right? All I'm doing in any chemical reaction is the same thing. I'm taking the parts I started with and I'm using them to do something else. But I'm not suddenly going like this and going, if I take lead and I add hydrogen, I can get gold. Okay? No, I can't do that. I didn't have gold to start with. I can't have gold at the end. I can't make a new element. I can make new materials, new compounds, okay? But I cannot make a new element with a chemical reaction. Okay, so that's what point number 4 says. It's kind of verbose, right? It kind of talks around this point, but this is effectively what it's saying. You cannot change atoms of one element into atoms of another element in a chemical reaction. Okay, a nuclear process, that's different. Okay, you actually could in a nuclear process, but this is chemistry. Okay, remember, Dalton is 1700s. Nobody even knows what the atom looks like yet. Okay, never mind being able to split it. Okay, do I need to know the 4 points for sure?
Yes.
Will they definitely be on a quiz and a test?
Yes.
Definitely. Okay, so make sure that those are something you have written down, they're highlighted, you know I've got to know these things. Do you have to be able to write them verbatim, word for word as they are on here? No. Okay, get the general point across, okay, with your 4 points and you're good on those. Okay, are there any questions on Dalton's atomic theory before I move on? Okay, so historically speaking, when Dalton came up with this theory, it was fairly universally accepted. Okay? It made a lot of sense. It explained a lot of the current research at the time and the behavior of matter. The natural follow-up question to this was, okay, John, what do atoms look like? And his answer was kind of, well, didn't you read my first point? It says they're really small. I don't know, I can't see them. I have no idea what they look like. People are like, well, that's kind of awkward. You sort of probably should know that. You probably have some idea. So, what's a good naturally occurring shape that we see? Spheres. All right. An atom is a solid sphere. Because at that time, we didn't know about protons, we didn't know about neutrons, we didn't know about electrons. It kind of made sense that things would be a sphere, right? Planets are spheres. By the way, the Earth is a planet and it's round. Yeah. If you're a flat earther, you're going to hate everything I say in this class. But okay, the Earth is round. Yeah. Okay, and that's the only way it works. So sphere was a naturally occurring shape. Okay. So yeah. Okay. Atoms are spheres, and everybody's like, okay, that works. Okay. And the model of the atom stayed that way for a while, probably close to 200 years. Okay. And then people started seeing in more in-depth experiments that model couldn't explain some of the things that were going on. Okay, and that's kind of what we're going to move to here is the process of how we changed our idea of what the atom looked like and why we did that, and why that's a good example of a scientific process. Okay. All right, so that was Dalton. Dalton said atom's a sphere. It's just a ball, everything. Every atom's ball is different, okay, but that's what they are. It's just a ball. Okay, so generally accepted over the years, okay, but now we know an atom can be broken down into smaller particles. This doesn't explain how the reaction that powers your phone, which by the way is a chemical reaction, works. This model can't explain that because it involves electrons coming off of atoms and flowing, okay, from one side of the cell to the other. Okay, so this doesn't fit with that. And that's exactly the research that was going on that led to the next model. Okay, a guy named J.J. Thomson was doing electrochemical experiments. He was finding chemical reactions that would produce electricity. Okay, these were the things that eventually led to the development of the dry cell and wet cell batteries, and eventually to your lithium-ion batteries that power most of our rechargeable devices. Okay, so in his experiments, he would combine two reactants, and as that reaction occurred, an electric current would flow through the wire. Okay, now the wire didn't get heavier. Okay, if the wire got heavier, then you could say that actual atoms of something would be traveling through the wire, but that would be really weird. Okay, because then your copper wire would like bulge and change color and do kind of weird things as atoms flowed through it. That wasn't what was happening. These were tiny particles. Okay, the mass in his reactions wasn't changing, which means these things were incredibly small that were moving through the wire. Okay, but he did notice that as the experiment went on, okay, electrons would collect on one side and come from the other. You'd have your anode and your cathode, okay, in a cell, the positive and negative ends. Okay, so he said, okay, the solid sphere doesn't explain that. So there's this other particle that's negatively charged, and then there must be something else that's positively charged because we know atoms don't have charges, right? They have a net overall charge of 0. So there have to be two different things that are charged. So he said, I'm going to take the solid sphere, because I respect Dalton and he knows what he's doing. Okay, and I'm just going to say that embedded very loosely, like kind of lightly stuck to the surface of this solid sphere, are these little particles called electrons, and they're negatively charged. And the sphere is positively charged. Okay, and so when my reactions occur, essentially these electrons get shaken off, and then they flow to another positively charged thing because negative things are attracted to positively charged things, and that's kind of how it works. Okay? And so the model of the atom changed. It's not great. It's not a great explanation of what was going on, but it was better than, here's this big ball that doesn't explain anything. Actually, not big, little, really small, tiny ball, okay, that doesn't explain anything. So we went to this, which we call the plum pudding model. Okay? Should you know the models well enough to recognize them on a multiple choice question?
Yes.
Yes. Okay? Am I going to be asking a lot about names and people? No. Okay? But as long as you generally know the models, okay, there's one or two people that would be important, like Dalton. You should definitely know him. Kind of important. Okay? All right, so this is the plum pudding model. The electrons are loosely embedded on the outside. They fall off in a reaction. That explains the electric current that can be generated by some chemical reactions. Now, we go through this phase in time after this where the model of the atom rapidly changes. It just starts to evolve because we really start to understand a lot more about the nature of matter, especially once we get into nuclear science and we start actually splitting atoms. Okay, you kind of got to know what you're splitting, okay, before you go at it. So, a lot of models came up. Not all of them were good. And there was actually a lot of disagreement. I think atoms look like this. I think atoms look like that. Okay, and there was actually a lot of disagreement in the physics and chemistry community about what atoms should actually look like, because we were discovering that not only are there these negatively charged particles, there's also positively charged particles. And if I only have those two things, matter's too light. It doesn't account for all the mass in an atom. So there must be something else in there that can help account for the mass. Okay? Maybe it's just still a solid sphere and there's, positive charges and negative charges and the rest of it is neutral and that's what makes up the mass. Or maybe there's another particle that's like the proton but it just doesn't have a charge. And so there was this argument between, is it still like a plum pudding but there's more plums and less pudding, or is there just actually a whole bunch of different particles in there, neutrons, protons, and electrons? Okay? And because atoms were small, there wasn't really a way to explain that until we started doing more studies on radioactive decay and things like that. Okay? All right, so discovery of the proton, okay, obviously meant that the plum pudding model wasn't going to work anymore, okay? And the discovery of the neutron, same thing. Okay, now we got to go away from anything that generally resembles the solid sphere and something to more like a true nuclear model. Okay, that there's this central nucleus and a lot of empty space. Okay, those kind of ideas were really at odds with each other. Okay, Chadwick discovered that protons were not the only large particle in the atom. He found that the mass of many elements was too large to be accounted for by only protons and electrons. His experiments proved the existence of a third and final subatomic particle, the neutron, which carries no charge or is neutral. Okay, so once that came along, as I said, any kind of thing about a plum pudding had to go by the wayside. And then there was argument about where are all of these particles? How do they behave? Okay, what are they doing? How big are they? Okay. All right, so the next experiment, this is another guy whose name you're going to need to know, okay? Because his experiment proved that an atom is actually a very small central dense nucleus surrounded by electrons. Okay? He essentially proved what we call now the nuclear model of the atom, that there is in fact a nucleus in the atom. Okay, so Ernest Rutherford, that's the name. Okay? He felt that atoms could not have all these particles floating around randomly. Okay? That an atom was not this like kind of fluid thing that protons, neutrons, and electrons just floated around in, because that didn't make a lot of sense. The protons and the electrons would naturally attract each other, and then there would be a glob of stuff together because of that attraction. So that really doesn't work. There's got to be something else to this. I think the protons and the neutrons, the heavier part, collect in the middle, and the electrons must orbit around the outside. The more electrons, the more orbits there are. It's not like planets, okay? They can kind of go everywhere and they just get spread apart because they would obviously repel each other. They have the same charge. So people are like, well, how are you going to prove that? We can't see them. So Rutherford said, okay, here's what I'm going to do. I'm going to take a piece of gold foil, okay? So like aluminum foil like you would use for cooking at home, but made out of gold, but like thinner than a Kleenex. All right, so only a few atoms thick, this sheet of gold foil. So here's what I'm going to do. if atoms have a small, dense nucleus, and he thought like incredibly small, okay, dense nucleus, and electrons surrounding them, then they're going to be mostly empty space. And if I shoot X-rays at this gold foil, some of them will get through, because they'll be able to go through the empty space. The particles, photons that come from X-rays, okay, are also very small. They would be able to fit between the atoms. Okay? People are like, okay, well, how are you going to prove that they got through there? Okay, well, here's kind of the time jump or generation gap that exists here. Cameras used to have this stuff in them called film. Okay, and when you push the button, the lens would open and the film would be exposed to light, and then the picture would be developed like a week later at the drugstore, wherever you would take the film to. Okay, so that's what he had. And what he did is he conducted an experiment that looked like this. Okay, so he had this photographic film wrapped around the gold foil. And then he had basically an X-ray machine positioned here in a gap. His idea was that he would shoot the X-rays at this gold foil, and because atoms would have such a small, dense nucleus, the vast majority of them would just go through, and he would get like a bright exposure spot here on the other side, because most of the X-rays would get through. Okay, it's the same process we still use to do an X-ray today, except it's digital. Okay, so we shoot the X-rays at your wrist. If you hurt your wrist, right? Your bones will block more of the X-rays, and less the other X-rays will go through the fleshy parts, and then we get this image of the bone. Okay, it's kind of the same thing here. Okay, he just predicted that he'd get a big bright spot here, and maybe the odd dot somewhere else that had maybe hit a nucleus and been deflected slightly. All right, what he discovered was actually a lot different. Yes, a lot of stuff got through the gold foil, but way more of it ended up hitting. He got other spots all over the place on his foil, okay, which actually led to him being able to calculate that the gold atom nucleus was a certain size, because he could infer how many particles were deflected and by how much, and then get some sort of kind of estimate of the size of the atom. So this is what he kind of ended up going with. He said, okay, the atoms are tightly packed in this gold foil, but there is a lot of space. Here's the nucleus. So yes, some of the particles got all the way through, but some of the particles hit the nucleus and bounced back. And he was so surprised by this that he actually said it was like shooting an artillery shell at a piece of paper and having it bounce back. Okay, which is obviously not something that would happen, but that's how shocked he was at how many of the X-rays were actually deflected. Okay, meaning the atom's nucleus was much bigger than he had thought it would be. Right? But this experiment did prove unequivocally that yes, atoms are a lot of empty space, but they do have a large, dense nucleus. All right, so summarizing, Rutherford, gold foil experiment proved the existence of a central dense nucleus. Okay. Now at this point you'd think people would be happy, right? It's like, oh, right, great. We know that there's a nucleus, we know the nuclear model is right. Well, you'd be so wrong. Because chemists and physicists, they can find stuff to fight about. Okay? So the next fight was, great, we know where the protons and the neutrons are. What are the electrons doing? They're just there. I mean, we know they're small and we know that they move, okay? Because they're kind of like planets orbiting the sun. They're attracted to this positively charged nucleus, and so they orbit it just like the Earth orbits the sun because it's gravitationally attracted to it. People were fine with that. Problem is that they didn't know what those orbits looked like or whether they were constant, like the Earth orbiting the sun or the moon orbiting the Earth. They didn't know. And there really wasn't a way to prove any one idea over another at that time. So Rutherford said, I think they look like this. This was the Rutherford model of the atom. Okay, there's that central dense nucleus, and then the electrons are all equidistant from the nucleus. The more electrons there are, the closer together the orbits will get. Well, there's a real problem with that when you start getting to, your bigger atoms that have nearly 100 electrons. There starts to be very little room. And the problem with that is electrons are all negatively charged and they repel each other, and that would cause all kinds of problems. So his idea of what the electrons did was actually quite quickly rejected. Okay? And we went to all kinds of different things, like the Bohr planetary model, which said that they actually do move in these circles and they orbit at specified distances and they kind of stay there. But if something happens, they can jump from lower to higher orbits. And that was actually widely accepted for a very long time, and we actually even still today draw them a bit like that. But we know that that's actually not the case either. It's not a circle, it's a sphere. It's 3 dimensions. Okay? It's not like the ecliptic model of our solar system where, you know, the planets could all line up and eclipse each other. That the electrons can't do that. They move around actually a bit randomly. Okay, so this was the Bohr model, okay, and it said that electrons orbit in orbits that are based on their energy, which is true. We do know that. They're the different levels or orbitals. We don't even call them orbits because they're not circular. Okay, orbitals is areas where you can find an electron. Okay, are based on the energy of that electron, and that electron's energy can change. It can go up or down, and then the electron would actually move to different orbitals. Okay, Bohr's model doesn't really explain that very well, but if you were to just take a picture of an atom and freeze it in time, it might look something like this, because you would freeze the electrons in one place and you wouldn't get an idea of what they're doing over time as their energy changes. Okay, so for simplicity's sake, we often draw an atom with the Bohr model because it's easier. Okay, but again, it doesn't explain how electrons can move about, so it was actually rejected shortly after. Okay, this is the one we currently accept. Okay, this is the model by de Broglie. Okay, and we generally call it the electron cloud, or sometimes the quantum model. Okay, quantum refers to energy levels. You can. Okay, now the thing we have to understand is that de Broglie's model, as it's depicted here, makes it look like electrons are just randomly everywhere, and they're not. Okay, when you get into Chem 20, actually like the second day of Chem 20, Mr. Riel or Mr. Batchik or Ms. Sikora will show you all these different orbitals and electron configurations that any one atom can possibly have. All right, so you would see that, yes, lots of the inner places close to the nucleus are going to be filled because they're lower energy and everything is going to naturally go to those easier points. But as they gain more and more energy, you are likely to find them further away. Okay, so we see that that cloud is dense near the nucleus, okay, but there are electrons in other places as well. Okay, and that is based on their energy. There's all kinds of weird shapes. I think I have a picture of it here on the next slide. Yeah, what some of those orbitals look like. Okay, so de Broglie was doing experiments about reactions that resulted in changes in energy of electrons. Okay, how many people have ever seen like glow-in-the-dark materials? Like you take them out in the sun, right, and then you move them into a dark place and they glow for a short period of time. That's de Broglie. That's explained by de Broglie's model. Okay, it's actually also how photosynthesis works. Okay, so you take that glow-in-the-dark material outside in the sun, or a plant is out in the sun. Okay, energy from the sun is striking the atoms, and what's happening is the electrons are gaining energy, and they're jumping from low energy levels to high energy levels. Okay, and they'll stay there or jump even further as long as that source of energy is there, giving them the energy to move. Once you take that glow-in-the-dark material out of the light and put it in the dark, there's nothing to hold those electrons there. They can't stay there. They start to slow down. And when they start to slow down, they tumble down into lower energy levels. And when they do that, they give off the energy they gained. In a glow-in-the-dark material, it's given off as light. And that thing will glow for a short period of time until all the electrons have fallen down to the original energy levels and have no more energy to give. Okay? For plants, same thing happens. Okay? The light hits the chlorophyll, okay? The electrons in the chlorophyll get excited, they hop up to higher energy levels, and then they fall back down, and when they fall down, that energy is used to make sugar. Okay? To break the carbon dioxide and the water up and put them back together as glucose. Okay? de Broglie's model explains that behavior. None of the other models can. Okay? And that's why we now currently accept the electron cloud model. All right? Okay. Anybody need that slide anymore? Okay, so, again, there's all kinds of different ways to kind of show that, but the big thing here is that atoms are actually made up of a lot of empty space. Okay? That cloud that contains the electrons is all considered to be part of the atom. Okay? In the same way that in our solar system, the Oort cloud, which is really, really far from the sun, is still considered to be part of our solar system. Okay? There's not much out there, okay? But it's still considered to be part of it. There's a lot of empty space.
So in the de Broglie model, when they lose energy, what's stopping the protons from kind of attracting them in?
Well, as they lose energy, they slow down, but they move to lower orbitals where their speed is now sufficient to keep them in orbit. I suppose if they were to lose enough energy, they could theoretically do that, but we've never seen matter really do that. You also have the neutrons in that nucleus, right? Compared to an electron, a neutron looks almost positive. Compared to a proton, a neutron looks negative, right? Because this thing is all positive, this thing is all negative, so there's a lot of strong inner atomic force that kind of keeps that exact situation from happening. There's a lot of repulsion and attraction and things like that that go on, if that makes sense. You'll learn more about it in Chem 30. Come on. Okay, so remember I was telling you about what some of those orbitals look like? Okay, this is what some of those orbitals look like. So you'd have your nucleus, that would be, you can see the protons and neutrons all down in here, all kind of clumped together. And then this purple circle here is what we would call the 1s orbital. The 1s orbital is the one that's closest. It can only hold 2 electrons because it's very, very close and they can't get too close together. Okay? And then as you move out, okay, you get your 2s orbital, which is simply a bigger sphere. Okay? Then you get your 2p orbitals, which kind of look like balloons. Okay? You get your 3s, and it goes on. It goes like way up to like 6p, and like one of the orbitals is a donut that goes around the middle, way out on the outside. There's all kinds of funky shapes to these orbitals, okay? And they're all based on how many electrons you have and how much energy they possess. Okay? So they can move into it. It's not like planets around the sun. It's also not random as a cloud, but because they can move anywhere, it kind of appears that way.
Do they move in a certain orientation?
Yes, they do. Because remember, if I get an electron into this orbital, it can't orbit in a circle, because if it does, it's going to encounter the other electrons which it's repulsed by, okay, in those orbits. So if in your 3s orbital, it's further out, right? So it's not going to interfere with these as the electrons move around in there. But remember, this is a 2-dimensional representation of something that is actually 3-dimensional. Right? So there's a lot of room to move, okay? And that's why it's not circles. Okay? You've got 2 electrons moving in different orbits, but they come close to each other, they're going to kick each other away. Right? All right, so first day of Chem 20, you'll learn all about the electron configurations of all the atoms, and that's apparently fun. I don't know. Okay? All right. So, oh man, it's slow today. Too far. All right, what I would like you guys to work on right now, it'd be that way, huh? I just have to be patient. All right. first page of the chemistry worksheet package, if you have it, is these questions. Okay, if you don't have that, I will put them up this way and it might be easier to see. Okay, so those are the 12 questions. Do they need to be bigger? I can make them bigger if you need to. Okay, this way they all fit on there. Okay, I want you guys to work on those, probably give you about, I don't know, till maybe 9:45, and then we'll go through them, okay, before class ends. So, okay, work on those here now in class. We'll talk about them in a little bit, kind of go through them all, and then tomorrow we'll start reading our ionic compounds. Questions?
Are you allowed to work with?
Okay, so question number 1, the idea of the atom was first proposed by whom? Who came up with that?
Democritus.
Democritus, right. The Greek thinker, okay, was the first person to say that matter is composed of tiny things called atoms. Okay, why was it rejected at the time?
Aristotle said that there were only proven that there was only 4 elements.
Right. Yeah, the 4 elements idea worked better. Okay, given the knowledge that people had, the experience that people had, the 4 elements idea made more sense. It was more easily explained. Okay, it was more easily basically just experienced in day-to-day life. So that was why it was rejected. No one believed something they couldn't see. Right? You could see the 4 elements. All right, question number 2. What elements did the Greeks believe all matter was made of? Well, we just said that. We just said it was earth, air, fire, and water, the 4 elements. Okay, and we also kind of talked a little bit about why that was a logical conclusion. It was something you could experience. You could put it in your hands. Okay, when you boiled water, you made steam by combining fire and water. Okay? It was something that made sense. It was logical because it was experiential to those people. Okay. During the Middle Ages, what do we call those people that inadvertently did a lot of work on chemistry?
Alchemists.
The alchemists, okay? And their goal was to?
Turn lead to gold and make the elixir of life.
Right, basically to get rich through better chemistry, okay? And, obviously they didn't work very well. They did come up with a few things, like even like things like alloys, okay? Would have been things that, the alchemists probably would have came up with. Making brass, which kind of looks a lot like gold by mixing 2 metals together, okay? But then there was that whole Archimedes thing where, the king thought he'd been ripped off, and then he got in his bathtub and he found that he displaced water, and that if he had an X amount of gold, it would displace this water. When he put the crown in, it didn't displace that much water, which meant it wasn't all gold. Okay, that was Archimedes' principle. Okay, so things like that, that was all during alchemy, and so discoveries were certainly made there. Okay, 1700s, a man used data from many experiments on matter to develop an idea on its structure. Who first? Dalton. Okay, first point of Dalton's atomic theory.
All matter is made of atoms.
Right, all matter is made of atoms. Okay, second point. Yes, you can.
Atoms of the same are identical, and atoms of any other element are different.
Exactly. Atoms of the same element are identical, atoms of different elements are different. Okay, third point.
Atoms in different elements can combine with other atoms of different elements to create compounds.
Right, to make compounds. So atoms can combine to make compounds. One thing I want to add to that because it's really important. Simple
numbered ratios.
whole numbered ratios, right. Okay, we got to make sure that whole number ratio thing is part of that. Here's why. It specifically then states atoms cannot be fractions. Okay, I can't have H1O1 half, right? That's the same ratio, 2 to 1, okay, but it's not a whole number anymore, it's 1 to 0.5, okay? It doesn't work, I can't have half of an atom, okay? All right, and last point.
Chemical reactions happen when atoms are separated, joined, or rearranged. You cannot make a new element in a chemical reaction.
Exactly. New elements can't be made in a chemical reaction, but existing elements can be separated, joined, or rearranged. Anything in there about, you can't make a new element, but you can do these things with the elements, that's good. Because it's kind of a long, that last point is kind of a long one. If you can summarize it, make sure you have those key points in it, then you're set. Okay, now looking at this theory now, okay, what do you know of that can prove some of the ideas wrong?
You can prove point 1 wrong because of nuclear fission.
Right, okay, we're able to split atoms now, right? And we actually know that some atoms actually degrade a little bit on their own, okay? Generally, the bigger an atom gets, the less stable it becomes, okay? That's why at the end of the periodic table, okay, we got all of these ones here. They don't even have like some of the numbers for them, or they don't have them very accurately because they last for such a short amount of time in a particle accelerator. They are like the Large Hadron Collider and things like that, that they just break down so quickly. And that they can't even be accurately measured. They have a half-life that's like fractions of a second, and they're gone. Okay, so the larger that the atom becomes, the more likely it is to just naturally lose neutrons here and there, and kind of radioactively decay. In fact, even smaller atoms do that. Things like carbon, for example. We use carbon dating to figure out how old things are because we know the rate at which carbon-14, not carbon-12, but carbon-14, okay, breaks down. Right? And we can then figure out, this artifact is this many thousand years old based on that. Okay, so that's the first one. Okay, what's another one? Anything else?
Like that the atoms are identical. They have the same properties, but they're not identical because the electrons move around.
Okay, the electrons move around for sure, and they could have different numbers of, not protons, but the other one. Neutrons, right, those isotopes. Yeah, I was just talking to you about carbon-14, right? Carbon normally has 12 protons has 6 protons and 6 neutrons, okay? 12 particles in the nucleus. Carbon-14 is an isotope of carbon that actually has 8 neutrons in it. Okay? Because of that, the atom isn't as stable and it loses the neutrons over time, radioactively decaying back down. Okay? That's the thing, that's why we can use it to determine the age of things. We know how quickly it breaks down into the other material, and we can look at how much carbon-14 there is compared to how much of the material it breaks down into there is and determine its age. Okay? So isotopes are other versions of those elements, atoms, that are not quite the same. They have to have the same number of protons, that's the sticking point, okay? But they can have different numbers of neutrons, and that is something that makes that part of the second point a little bit iffy, okay? All right, now, so we can split an atom. How do we do that? How many people seen Oppenheimer? How'd you get in? Isn't it really dark? Okay, so in a fission process, okay, there's kind of 2 ways to do it. In a bomb, you want it to go out of control. Okay? You want the chain reaction that causes the splitting of the fissile material, okay, to happen exponentially and obviously cause death and destruction. Okay? In a nuclear power plant, you generally don't want that. You want the reaction to be controlled. Okay? So in a nuclear power plant, what we do is we have fuel rods, which are exactly as you would think they would be based on their name. They're a metal rod. Embedded on the surface of that metal rod are fuel pellets. Okay? And those fuel pellets contain enriched uranium. Right? What we do is we lower those fuel rods into a water bath. Okay? And then we have an emitter that fires basically like free neutrons or alpha particles at those fuel pellets. And when it hits them, the fission reaction begins. And it releases heat, which then boils the water, turns it into steam, and the steam turns a turbine, okay, and generates electricity. Okay? In The Martian, Okay, if you recall, Mark Watney went and dug up the big chunk of plutonium. Now, they said specifically, Mark, don't go dig up the big chunk of plutonium, but he did anyway. Okay, that's a radioactive decay generator, which simply uses the heat generated from radioactive decay to generate heat in a thermocouple instead. So it's more direct, okay? But we generally don't put it next to people too much, which is exactly why he was told not to go get it, but did anyway. Okay, we use it to power lots of spacecraft, the Voyager spacecraft and things like that that are way out. They're still running on the ones they put in them back in the 60s. Okay, so they can last for a pretty long time. All right, but most of our fission power is generated by heating up water, turning it into steam, and having that steam turn the turbine. Okay, the only problem comes here is if something happens and all the water evaporates, and now there's nothing to cool the rods. The rods get hot enough, then the chain reaction will start, and you'll get a meltdown. Okay, which is exactly like it sounds. Everything just melts because it gets really, really hot, and then you get that big elephant foot thing like they have at Chernobyl. Okay, so generally, as long as the coolant is there, the water is there, okay, everything is fine. Okay, if you want to generate more electricity, you simply lower the rod further in and expose more of the fuel pellets to the particles, and more fission occurs. Okay, if you want less, then you put in more water, or you raise the fuel rod out. Okay, so that's kind of the controlled version. Okay, in a nuclear bomb, well, you kind of want that to happen quickly. So basically what you do is you have a bunch of high explosive, plastic explosive, C4, something like that, okay, surrounding, so you have like a shell basically of high explosive that's focused inwards, and then you have your chunk of fissionable material in the middle. This is very basic kind of how you could never build a bomb with these instructions, which is why it's safe for me to put it on YouTube. Okay, but basically what you have here is two explosions. You have a small one that causes this outer shell to explode, and all of that matter gets accelerated towards the fissionable material at a high rate. And when it hits it, some of the atoms start to break. And when they break, the pieces of them go off and break the one next to it, and you get that chain reaction that leads to the giant mushroom cloud death. Okay, so kind of like that. Again, that's about as far as I can explain it, because that's about the end of my understanding of it. Okay, and plus then I would get like taken off of YouTube for giving instructions on how to build nuclear weapons. No question? No. Okay. All right. So those are kind of the points that don't really fit anymore. Like, yes, for all intents and purposes, an atom's not divisible. Okay. Only really big ones that are kind of unstable are. Okay. And we can use them for that. Okay. And then of course the isotope thing as well. All right, now, the models of the atom, okay? What did we start with? What was the first one? The solid sphere, right? Which was fine because we didn't know anything about any of the other particles. It just explained that matter is solid, and here it is, okay? But then as experiments continued to occur and their results couldn't be explained, we did the right thing, which was, okay, that model doesn't work anymore. We have to change it, okay? And that's how science is supposed to work. Okay? Chemistry and physics did that with the model of the atom. Biology is a good example of how not to do this. Okay? Your parents, okay, probably learned that all life on Earth fit into two kingdoms. You were plant or animal. Okay? Now, currently, there are 5. Okay? Because that's the way it should work. Okay? But everything just fit into 2 kingdoms before. Okay? Mushrooms were plants. Well, that's terrible. Do mushrooms carry out photosynthesis? No. No. By definition, to be a plant, you have to carry out photosynthesis. Guess what else was in the plant kingdom? Bacteria. Not all bacteria are photosynthetic. They don't belong in there. And they're single cell. Plants are multicellular. Okay? But there was this idea that 2 is good. You're plant or animal. We'll just jam things in whether they fit or not. Okay? Mushrooms go out of the ground, so they're plant. Jam them in there. Rather than go, is there a better fit? Could we make something else for these? Now, mushrooms and all fungi have their own kingdom. Okay? And protists, like amoebas and things like that are single-celled. They're not in the animal kingdom anymore. They're in their own kingdom. Okay? We didn't just try to push a round peg into a square hole. Okay? With the model of the atom, we said, this model doesn't work. It's either got to be modified or it's got to be rejected and we got to start over. Okay? So Thomson's plum pudding model was simply a modification. Yes, the solid sphere wasn't perfect, but he could still use it, and so he modified it to have the plums, the electrons, loosely embedded on the outside. Okay? But the discovery of protons, that's a do-over. Okay? The plum pudding model can't explain that at all, so that is completely rejected. Solid sphere is completely out. Plum pudding is completely out. We got to start over. Where are these particles? How big are they? And each time we discovered something new, we continued to modify. Okay? Then Rutherford comes along. Rutherford discovers that there is a central dense nucleus. We get an idea how big everything is. Okay? Then de Broglie starts doing his experiments. We discover where electrons should fit into all of this. Each time, something is changed about the model to fit our better understanding. That's how science is supposed to work. Okay? If you have something along that line as a kind of general explanation of the progress, that's all I was looking for that. Okay. All right, the parts of the atom. Protons, what charge are they?
Positive.
Where are they? Okay, neutrons? In the nucleus. Electrons? And they're negative. Okay, at this point I want to go over something that will definitely be on your quizzes and tests. Okay, so you're going to want to write this down. Let's draw an atom of beryllium. Okay, so if I want to draw an atom of beryllium, okay, what I've got to do, I got to give you guys your periodic tables. You won't be able to. We'll do it tomorrow. Remind me, tomorrow you get your periodic tables. Okay, so if I want to draw an atom of beryllium, how many protons am I going to draw?
4.
Okay, how many neutrons am I going to draw? 4. How do I know? Well, actually, no. 5. I'm going to draw 5. Okay, because this number tells me the number of protons and the number of electrons, because they have to be equal. Okay, and then this number allows me to calculate how many neutrons. This is the mass. Electrons basically play almost no part in the mass of an atom, okay, because they're so incredibly tiny. So when I take this mass and I subtract the number of protons, whatever's left is the mass of the neutrons, or the number of the neutrons. So 9 minus 4 is 5. All right, so if I was just going to draw that, I would just go like this. I would say protons. I'd make a legend, because that's important. Okay, and okay, something like that. I've got a legend, now I know what everything is. And then I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'd go 1, 2, 3, 4. Okay, the rest of those are neutrons. And then I would go like 1, 2, 3, 4. And write cloud outside of it so that you knew I wrote the correct model. Okay, in case I couldn't tell that that was a cloud. Okay. There you go. I just drew a proper diagram of an atom of beryllium. Okay, that would be a 5-mark question. Okay, that's a gimme. Okay, for a 5-mark question, that's a gimme. All I'm looking for is number of protons, number of neutrons, number of electrons, all of them in the right place, and the cloud model. 5 marks. Okay.
Do we circle the neutron?
You can do whatever you want for neutrons. Some people draw a circle with an N inside.
The nucleus or what?
I just kind of drew them all together, but you could if you wanted to. Yeah. Okay, making sense? All right. All right, for number 8 here, it says 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. Assuming those 1 cubic centimeters had the same number of atoms, why is the lead heavier?
I have a question.
Oh, okay, sorry, what's the question?
So it's neutrons that orbit?
No, electrons that orbit. Yeah. Okay, we'll finish that up tomorrow, guys. So we're on question 8. We'll finish up the rest tomorrow in class. Good work today.